This video goes over how you should be approaching inclined plane problems for the MCAT. If you're looking for more MCAT help, check out the rest of this YouTube channel or the link in the description of this video to look at my self-paced course. In this video, we're going over inclined plane problems, and specifically we're looking at how should we set these problems up. When we set these up, we will have a second triangle, and we'll talk about what that triangle can be used to tell us. Then we'll look at how much force is needed to stop this object from moving down the inclined plane. Then we will look at how much friction is opposing the motion of this block moving down the ramp. For inclined plane problems, they are usually going to be giving you these details. They will give you some angle, and they're going to give you the mass of the object. Using those details, you're going to draw the second triangle. Do this by first drawing a straight line down, and then you want to draw a line that is perpendicular to the incline. This next part is really important, and people forget this a lot. You want to make this triangle that you're drawing a right triangle, and the 90-degree angle of the right triangle needs to be over here, so it needs to be on the same side as the 90-degree angle of the original inclined plane. Now just connect the two lines that were perpendicular and straight down. This angle theta will be the same angle of the second triangle right there. We have set up our problem and made our second triangle. Now we need to talk about what does the second triangle tell us, what can we use it for. This line that is going straight down, that is in the direction of the force of gravity on our object, which has a mass of m. That means we can find the force of gravity on this object by doing F equals mg. So this side of our triangle will have a value equal to mg, which for the MCAT will just be the mass of the object times 10. Let's say for this example, the mass of this object is equal to 10 kilograms. That makes the force of gravity on this object 10 times 10 because g is always equal to 10 for the MCAT. So the force of gravity on this object is 100 newtons. Since you're usually going to know the angle of this triangle, you can then use the force of gravity and the angle and some trigonometry to find the missing values for this triangle. First, let's look at this side right here and how you would find the value for that side. That side is adjacent to the angle, so the way you set this up is to do cosine of theta equals adjacent over hypotenuse. The hypotenuse of that triangle is the force of gravity, so we do cosine of theta is equal to adjacent over force of gravity, which we solved for our example to be 100 newtons. Then you take that force, move it to the other side, and we would end up with 100 times cosine theta equals the adjacent side. So this is ultimately how you solve for the missing value of the adjacent side of that triangle. I'll write that in on that side. Now, what does that side of the triangle tell us? Notice that that is the side of the triangle that is perpendicular to the actual inclined plane. If you need a refresher, go back and watch the video that covers normal force more on this, but remember that the normal force is the force that opposes the force that the object exerts perpendicularly to the surface. That means that if we take our object and we figure out how much force is it exerting perpendicularly against the inclined plane, then the normal force will be opposing that and be equal in value. We find the value of that by using the equation over here, meaning we can set normal force, or I will put Fn, equal to 100 cosine theta. And remember that we got the 100 value by doing the force of gravity, so for other triangles in any situation you end up with mg cosine theta is equal to the normal force. Now how about the other side of the triangle? That side is opposite of our angle theta, so we will do sine theta equal to opposite over hypotenuse. For our example, the hypotenuse is equal to 100, so we have sine of theta is equal to the opposite side divided by 100. That makes 100 sine theta equal to that side. Now we can write that by that side of the triangle. Just like before, let's talk about what does that side of the triangle actually tell us. Notice that that side of the triangle is pointing in that direction, and if we were to draw that same direction line on the object that's on the inclined plane, it's pointing straight down the inclined plane, and it's parallel to that surface. What this value is the portion of gravity that's pulling the object down the ramp. I always like to call that force of sliding, so I will put down by that side of the triangle that 100 sine theta is equal to Fs for force of sliding. That is the force that the object is sliding down the inclined plane with. So both of these values that we solved for we're reliant on first remembering that the hypotenuse of the triangle, the line that goes straight down, is just the force of gravity on whatever object you have on this inclined plane. And then from there, you just use really basic trigonometry to figure out the value of the other two sides. And remember that 100 was just specific for this problem. So for any other problem, the general rule is it's mg sine theta is equal to the force that's pulling the object down the ramp, or force sliding. Those are all the things that you can use the second triangle to tell you, and now we will look at how to figure out how much force is needed to stop the object and how to find the friction force on this object. We have a clean inclined plane here, and let's practice drawing the second triangle. First, draw the line straight down. We know that that line is equal to the force of gravity, which is mg. The second line is perpendicular to the inclined plane, and then we know that we need our right triangle to be right there. The final line just connects the first two lines that you drew. For the line that is perpendicular to the ramp, we already established that that is equal to mg cosine theta, and that is the normal force. For the other side, we established that that is equal to mg sine theta. We said that is the force sliding, which is the force pulling the box down the ramp. And theta would be right here on the second triangle, and it is equal to this angle of the original inclined plane. Now, let's address that first question of how much force is needed to stop this object from sliding down the inclined plane. As we know, the force of gravity that's pulling the object down the ramp is mg sine theta. If this is a frictionless surface, for the situation we have drawn here, this is the only force present. So that means the box will be moving down the ramp with that amount of force. And in order to stop that, we have to apply a new force. I will say FA for force applied to the box. If we want to stop the box from accelerating down the ramp, we would have to push against the box in the opposite direction. This force could be in the form of a rope that maybe is attached to the box right here, and it's pulling it back up the ramp, or maybe there is a little stick figure here, and this stick figure is pushing against the box there. In either case, the force being applied has to be equal to that force of sliding to create a net force of 0. So when the force applied is equal to Fs, that makes the net force equal to 0. Anytime you have a net force of 0, using this equation here, F net is equal to ma, we know that the acceleration would have to be 0 if the force net is also 0. What all of this shows is that all you need is a force equal to the force that pulls the object down the ramp. When you have that, your net force is 0, and then your acceleration of that object is also 0. So if the box was already moving down the ramp and then you apply that force, the box will continue to move down the ramp, but the acceleration would be 0. If we wanted to stop the box from moving down the ramp, we would actually have to apply slightly more than the force of sliding, because we would have to create a negative acceleration to slow the box down. But if the box is starting from a standstill, then all we have to do is apply the same amount of force as Fs, and that would stop the box from moving at all. Now let's erase all this and look at the friction force. Currently, like we said earlier, this object only has a force that is pulling it down the ramp, and that force is equal to mg sine theta. Friction always opposes the motion of an object, so our friction force is going to be pointing in the opposite direction. The force of friction is always equal to the coefficient of either static or kinetic friction. Let's say our object is not moving, and we will use the coefficient of static friction here. We do the coefficient of static friction times the normal force. We've already established how to find the normal force, and we would just plug that value in. So the maximum static friction would be equal to the coefficient of static friction times mg cosine theta. Now remember back from the friction video that this is the maximum static friction. In an MCAT problem, they would indicate this by saying something like, this object is on the verge of moving, meaning that whatever force is trying to move the object is equal to the maximum static friction force. I'm not going to explain the difference between the maximum static friction force and any friction force lower than that, but you can go and watch the video on friction to get a more in-depth explanation. Now let's take this equation that we have for the maximum friction force, and then we're going to apply the equation that we have for the sliding force. If the problem says that no other forces are involved and the object is on the verge of sliding, we know that the forces pulling the object down the ramp, which we've established are Fs for the force of sliding, we know that that force would be equal to the force of friction, which is preventing the object from sliding, and that's why it's on the verge of sliding but not yet moving. Then all you would do is plug in the equations that we've established for each of those. The force pulling the object down the ramp is mg sine theta, and the force of friction is the coefficient of static friction times mg cosine theta. And the mg cosine theta, remember, is just the normal force. What a lot of MCAT problems will do is take this base idea and then overcomplicate it by just adding a couple more forces. One of the most common and easiest ways that they'll do this is they will say that some force, so I will put the stick figure, is also pushing against the object. And the combined force of friction and the force of this person pushing against it, which I will do Fp for the force that the person is pushing against the object with, both of those forces combined are keeping the object at a standstill. All you do is add up those two forces on the right side of the equation, and we say that those two forces added together would be equal to the force that is pulling the object down the ramp. There are all kinds of ways that they can manipulate this, but the base equation of the force pulling the box down the ramp and the friction force opposing that motion, that is where you're going to start for most of these. One tricky thing that can happen is if the object is moving up the ramp because some force is pushing it that way. Then that means that the friction force is actually going to switch and oppose the motion of the object by pointing down the ramp. When that's the case, you just take the friction force part of your equation and move it over to the other side. If this video has been helpful, but you would like some additional examples on how to apply this, let me know in the comments, and then I will probably make a follow-up video for that reason.